Mr. Carlson here. Let's talk about forces in two dimensions. This is going to be example 13 from your notes. In this example, it says that Jonathan asks Billy if he can help lift one of his favorite boxes up a hill. The box is 1.3 kilograms. Billy exerts a force of 7 newtons, and Jonathan exerts a force of 11 newtons in this direction. And Jonathan's force is exerted at an angle of 28 degrees with the vertical. The first part of the question says, at what angle, with respect to the vertical, should Billy exert his force if the box is to accelerate straight upward? So we want to know at what angle right here, we're trying to determine this angle right here, in order for this box to accelerate straight upwards. The first thing we're going to have to do is we are going to have to break up each of these forces into their components. I can only do that with this force since I don't know the angle here. I'm not going to be able to break this up into its components yet, but I can break this one up into its components. When we're talking about components, remember what this means is this 11 Newton force here that's at an angle, we can think of it as breaking it up into its vertical component. In other words, part of this 11 Newton force, part of it is lifting the box straight up, and another part of this 11 Newton force is pulling the box to the right. So this 11 newtons we can break up into the horizontal one, or the x-axis, and we can break it up into the vertical one, or the y-axis here. So I'm going to redraw this over here, that 11 newtons. And what I'm going to do is I'm going to make a right triangle with these components. So what I'm going to do is I'm going to take this component here, this dotted arrow that I've got, and I'm going to bring this up so that it connects from here to here so that I make a right triangle. So I'm going to make a dotted line here. And again, that's just moving this up here. And then I'm going to leave this dotted arrow like this. And there I've got my right triangle. And the reason why I do that is we're going to use some trigonometry here to figure out what amount of that 11 newtons is pulling the box this way and what amount of that 11 newtons is pulling the box upwards. The reason I want to do that is because if I know how many newtons of force is pulling the box straight to the right, well, I know that it has to equal out on this side. So Billy has to be pulling this way. This component has to be equal to this one. And the reason we know that is because we want the box to accelerate straight up. We don't want it to accelerate to the left or to the right. And for the box to not accelerate to the left or to the right, these forces have to be balanced. So let's come back to this. And in fact, before we do that, I'm going to write up here, SOHCAHTOA, because we are going to need to use these functions in order to solve for part of this. So I'm going to label this so we know that this part of this triangle is 11 newtons here. I know that what I'm going to label this is the x component of this. So I'm just going to put Fx, so force in the x direction, and then this one I'm going to label force in the y direction. But again, these two are components of this one. So using our trigonometry that we've got up here, if I look at figuring out this force right here, force in the x direction, so that's going to be the opposite from this angle. So opposite over my hypotenuse is what I'm looking at. So it's going to be the sine function here because sine is opposite over hypotenuse. So when we set up our equation, sine of the angle, 28 degrees, is equal to my opposite side, so f of x, over the hypotenuse, which is 11 newtons. And so when I solve for this, I'm going to be multiplying by 11 newtons here, multiplying by 11 newtons on this side. So my force in the x direction is going to be, let's see, got to do this in my calculator here, sine of 28 times 11, so 5.2 newtons. That's the amount of force that is pulling to the right. So I know that over here, Billy, he's pulling with 7 newtons at some angle, but I know this component has to be 5.2 newtons as well in order for this to accelerate straight upwards. These have to be balanced. So now what I'm going to do is I'm going to take this triangle here, and I'm going to draw this down here. So we've got Billy pulling with 7 newtons. Is that my hypotenuse of that triangle? And I'm going to do the same thing again. Is I'm going to take this component, I'm going to bring it straight up like this, and I'm going to make that right dotted line. Make that right triangle. And then another component here. That didn't work out too well. This angle is what we're trying to figure out right here. And so I know this part of the triangle, right? We just figured that out, is 5.2 newtons. And so now I want to figure out this angle. So I come back up here, and right now what I've got is the opposite and the hypotenuse. And so opposite, hypotenuse, so I'm using this again. So sine of angle theta is equal to 5.2 newtons over 7 newtons. And so now I just want to solve for this right here, the angle. The way to do that is I'm going to have to multiply each side by the inverse sign. So if I multiply this by the inverse sign, that's going to get rid of that sign there. And I'm going to do the same thing to the other side. So let's punch that in our calculators and see what we get here. So 5.2 divided by 7, and then multiplying that by inverse sine. So I get 48. The angle is equal to 48 degrees. So that would be my first answer for the first part of that question, would be he has to pull at an angle of 48 degrees from the vertical in order for this box to accelerate straight upwards. He's going to have to pull at an angle of 48 degrees. The second part of the question, part B, says, with what acceleration does the box rise? So now we're going to have to use Newton's second law. Remember Newton's second law? And I'm going to erase some of this stuff here. Let's give us a little more room. But if we want to figure out, I'm just going to put that this is 48 so I don't forget, 48 degrees. We want to figure out the acceleration of the box upwards. Newton's second law says that the acceleration is equal to the net force that the box is experiencing divided by the mass of the box. I know what the mass of the box is, 1.3 kilograms. The net force, though, what I need to do is I need to account for all the forces that are acting on this box. Now, the only forces that I'm interested in, since it's accelerating straight up, I'm interested in the forces in the vertical direction. I don't care about the forces in the horizontal direction. So now what I need to do is I need to figure out what's the total amount of force pulling straight up on the box and the force that's pulling straight down. For the force that's pulling straight down, we know that that's going to be the force of gravity. So that's just going to be the mass times acceleration due to gravity. So 1.3 times 10 meters per second squared is going to give us just 13 newtons. So there's 13 newtons pulling down. I need to now figure out how many newtons are pulling straight up. Well, I've got this 11 newtons pulling this way, so now I have to figure out this component of that 11 newtons of force. I have to figure out how much of that 11 newtons is pulling straight up on the box. The way to do that, I need to get rid of this, and now I need to get rid of that. Coming back to this, so I already figured out this component using the sine function. Now what I need to do is use cosine, right? Because cosine is adjacent times the hypotenuse. And so we're going to do cosine of 28 degrees is equal to the adjacent angle, Fy over 11 newtons. And so multiplying by 11 newtons on each side. My force in the y direction, let's see, 28 cosine times 11 is 9.7 newtons. So on this side here, so I'm going to make a note that on this side, coming from Jonathan, that's 9.7 newtons coming from him. I'm going to do the same thing over here. I got to figure out this part of that triangle there. So we're going to do, well, we could do this a couple different ways, but let's stick with these functions up here. So I've got the opposite side, and I've got the hypotenuse, so I could choose a couple different ones here. I'll use this tangent one right here. So tangent of this angle is going to be equal to opposite over adjacent. So I know the opposite one. I'm trying to figure out the adjacent one. So let's plug that in. We know that the angle, so tangent of 48 degrees, is going to be equal to opposite 5.2 newtons over the adjacent angle, A, we'll say. And so to solve for this, whenever we've got an equation that looks like this, where I've got the variable that I want to solve for in the denominator like this, I can just swap these out. So A is going to be equal to 5.2 newtons divided by tangent of 48 degrees. Let's plug this in and see what we get. 5.2 divided by tangent of 48, and I get 4.7 newtons. So from Billy on this side, pulling straight up, the component of that 7 newtons is 4.7 newtons pulling up. So now the force, the total amount of force that's pulling up on the box is going to be these two things added together. So we're running out of room here. So the total amount of force, let's see, 4.7 plus 9.7 gives me 14.4. So I've got a total of 14.4 newtons pulling up. So that means my net force in the vertical direction here is going to be 14.4 newtons minus this 13 newtons because they're acting in opposite directions. So 14.4 newtons minus 13 newtons, and we should get 1.4. That's the net force after these are canceled out, and so now I can use this Newton's second law to figure out what the acceleration is. So the acceleration would be 1.4 newtons, the net force, divided by the mass of the box, 1.3, kilograms, not newtons. And newtons per kilogram, remember, is the same as meters per second squared. They're both an acceleration. So 1.4 divided by 1.3, and we get 1.1 meters per second squared. And so that would be the acceleration of the box going straight upwards. The final part of that question there in your notes says if Billy starts to lose focus, remember Billy is this one right here, this 7 newtons of force, and he's pulling at a greater angle than Jonathan is. So for Jonathan, his rope that he has is kind of closer to the vertical, and Billy's is a little further away from the vertical as they're pulling. If Billy starts to lose focus and the angle of this rope starts to increase, how will the box start to move? So let's say he's still pulling with that same amount of force, but he starts to pull further this way. We increase this angle. Well, if that happens, that means more of this number right here, is going to get bigger, isn't it? So if he starts to lose focus and this angle starts to get bigger, meaning he's pulling further and further down this way, this number is going to go up, and now I'm going to be unbalanced in the horizontal direction, and so it actually would start to accelerate this way as well. In other words, it would kind of start to maybe accelerate at an angle this way. For the next part of your notes there, example number 14, we're going to go down here. In this one, it says we've got 2 crewmen. Here's crewman 1, crewman 2. They pull a boat through a lock. So this situation is like a bird's eye view, like we're looking down on it. One crewman pulls with a force of 130 newtons. That's this one right here, 130 newtons. And it says it's at an angle of 34 degrees. That should say it's an angle with the vertical. So this angle right here would be that 34-degree angle. The second one on the opposite side of the lock pulls at an angle of 45 degrees. So his angle here is 45 degrees. With what force should the second guy, this one, the second one. Oh no, I don't know what happened here. Whoa. Let's redo that. Second one, first one. What force should he pull so that the net force is in the forward direction? Kind of like the previous one, except for in the previous one we're solving for the angle. In this one we're solving for what force does he have to have in order for this to go straight forward, for it to move straight this way or accelerate this way. So in the last one we said that the horizontal forces, the components, have to equal out. Same thing in this one. So I'm going to take this triangle that I can make with the components of this 130 newtons. I'm going to draw this over here. So 130 newtons. And I'm going to bring this arrow over here. The reason I'm bringing this one over here to make this triangle instead of bringing this arrow up to make that triangle, I could do it either way. The reason I'm bringing this one over is because this is the angle that I'm given. I'm given this 34 degrees. So that's why I'm going to bring this one over so that I'm using this angle. Anyways, let's set up that triangle here. So we've got in the y direction, and we've got in the x direction, and here's our angle of 34. And right now, let's figure out what this force is right here. So the force in the y direction. Once again, I'm going to rewrite this because I always forget unless it's staring me in the face, and then I know. So let's look. We're looking at opposite over hypotenuse. So that's going to be the sine function again. So sine of 34 degrees is equal to Fy over 130 newtons. So this is going to be sine of 34 degrees times 130 to figure this out. So this works out to be, let's see, sine of 34 times 130. And I get, let's see, we'll say 73. We'll just round it to 73 newtons. So that's, this force here is 73 newtons this way. And so we know that this part here has to be 73 newtons. And so now I'm going to take this triangle here. So I'm going to redraw this one down here. We've got the force that we're trying to figure out. I'll just label it H for the hypotenuse. We're trying to figure out what that force is. And I'm going to bring this force over this way. So right here, right here. This is our angle of 45 degrees. I'm going to get rid of that H real quick, and I'm going to put it on the outside of this triangle. H. All right, and we've got Fx, and we've got Fy. We know that this one right here has to be, so actually I'm going to erase that as well because we know that that one has to be 73 in order for everything to balance out. So this one is 73 newtons. So let's see, I've got the opposite side, and I want to solve for hypotenuse, so we're going to use the same thing, except for this time it's going to be sine of 45 degrees is the angle that he's pulling at, is equal to my opposite side, 73, over what I'm trying to figure out, the hypotenuse. And so again, I've got my variable on the bottom here. So what I'm going to do is I'm going to swap these two things out. So the hypotenuse is going to be equal to 73 newtons divided by sine of 45 degrees. Let's punch that in and see what we get. 73 divided by sine of 45, and I get 103 newtons. And so he's going to have to pull, if this guy's pulling at 130 newtons at an angle of 34 degrees, this guy's going to have to pull with 103 newtons at an angle of 45 degrees. The next example there in your notes, it gives us this multiple choice question here. It says we've got this box that we are pulling at a constant velocity, and we're pulling on this box at some angle. So here's they label it with a P for this force here, but we're pulling on this. And then we've got the normal force, we've got the force of friction, and then we've got the weight of the box, which would just be mass times gravity. Here are my choices. In order for this to move at a constant velocity, which of these has to be true? Well, let's think about this. We've got P, the force, the pulling force, has to be greater than F, and the normal force has to be less than weight. Or we can have the pulling force is greater than F and the normal force is equal to the weight. Or pulling force is equal to the friction and normal force is greater than the weight, so on and so forth. So let's first think about it in terms of normal force and the weight. How about that? If the normal force was equal to the weight in this case, if this force and this force were equal, well, that means the box would actually be accelerating upwards. It would be being lifted off the ground. And the reason we know that is because if this force and this force were the same size, I've also got this force happening here, which, remember, we could break up into its components. This pulling force is acting upwards and it's acting to the right. And so if this and this were equal, that means my net force would be upwards because I've also got this. I would have more force pulling upwards, and so the box would be accelerating upwards. So I know that any of the choices where it says that the normal force is equal to the weight, those cannot be. Those will not work out. So I'm going to cross out the ones where it says the normal force is equal to the weight. And so now I'm left with these right here. And if I look, it says normal force is less than the weight and normal force is greater than the weight. And we just got done saying that really we can think about it, this and this have to add together to equal this. And so really that normal force must be less than the weight. And so really my only option left would be this one right here. Normal force is less than the weight. But let's think about it in terms of the pulling force and friction. If the pulling force was equal to the friction, so if this one here, this force here, was equal to this, that means this force here, this component right here, this component is going to be less than whatever this is. And for this to be moving at a constant velocity, I need this component of the pulling force to be equal to friction. The only way I can ensure that this component is big enough to be at least equal to this, that means the force that I'm pulling with needs to be greater than that force of friction. Because this force right here is going to be, once it's broken up into its components, this is going to be a little bit less than what that pulling force is. So this would be my only option that works for that one. And this is where we're going to end talking about these components for now.